Okay, students, you are welcome to this session. It is session 2 of Unit 2, so of PCK. This time around, we are looking at relative atomic and molecular masses, Faraday's constant, and molar volume. So let's get started. Let's look at our objective. Okay, so in this session, we will define relative atomic mass, relative molecular mass. We'll calculate molar masses of different compounds. We'll solve problems involving molar masses, moles, and masses. We'll define molar volume of gases. We'll solve problems involving molar volume. We'll define Faraday's constant. And finally, solve problems involving Faraday's constant. Our first objective, relative atomic mass. Now, with relative atomic mass, we are talking about the average mass of one atom of an element compared with 1/12 the mass of one atom of carbon-12. How can we do this mathematically? Relative atomic mass is given as the average mass of one atom of element over 1/12 the mass of one atom of carbon-12. So that's our definition of the relative atomic mass. Similarly, relative molecular mass, we are just removing the atomic mass and we are putting molecular mass there, or we are removing atomic and we are putting molecular there. So it is also the average mass of one molecule compared with 1/12 the mass of one atom of carbon-12. We can also do that mathematically, just like the relative atomic mass. This time around, it is a molecule, and when we do that, what it means, for example, is that if the relative molecular mass, sometimes referred to as the molar mass, of ammonia is 17, then ammonia is 17 times as heavy as 1/12 the mass of one atom of carbon-12. Now, in some cases, when we are finding molecular mass, the relative molecular mass will not add the relative, so that it will just be the molecular mass, and in that case, we will add units. The next thing is to look at molar mass, and the molar mass is the mass of 1 mole of a substance. So this is how to picture it. We are saying that 1 mole of a substance contains 6.022 times 10 to the power 23. Let's assume that I have a balance, a weighing balance, and let's say I have oranges and I'm weighing. If I count 6.022 times 10 to the power 23 oranges onto the balance, then whatever mass that the balance will record for me is the molar mass of the orange. So now, for example, if I have sodium and I'm able to count the sodium particles, let's say I have my balance. I pick one particle, I place on the balance. I pick one particle, I place on the balance. If I pick Avogadro's number, that huge number, onto the balance, then whatever mass that the balance is going to record for me is my molar mass. And so it has a unit, grams per mole, grams in 1 mole of a substance. Here we can do some calculations. We can find the molar masses of some compounds. For example, let's look at the molar masses of water, sulfuric acid, sodium carbonate, and carbon dioxide. Now, to do this, we need the atomic masses, or the relative atomic masses, and for that, hydrogen has been determined to be 1, oxygen is 16, sulfur is 32, sodium 23, and then carbon 12. Now, this is how to go by such situation. For example, we want to find the molar mass, which is represented by capital M, of water. So what we are going to do is we'll go for the atomic. We are looking at all the atoms in the water, so we'll pick them one after the other. We start with what we see first, which is hydrogen. So we pick the atomic mass of hydrogen, which is 1. Then we multiply it by the number of hydrogen atoms present. In this case, we have 2. So we are done with the hydrogen. Then we proceed with the oxygen. So atomic mass of oxygen, which is 16, times the number of atoms present, which is 1. And then we sum them together. Whatever we get is the molar mass of the water. And we can do same for the rest of the examples. Now there is a relationship between molar mass, number of moles, and mass of a substance. If you remember, we said molar mass is the mass of 1 mole of a substance. So even in that definition, we hear of 3 terms: mass, mole, in there. So let's look at the relation. The relation is that amount or number of moles is mathematically given as the mass over the molar mass. So small m for mass, capital M for molar mass, and small n for number of moles. Let's try some questions. Let's start with this, where we are to find the number of moles in 12 grams of sodium atom. Remember, this time around we are not looking at entities, we are not looking at particles. So we don't need Avogadro's number here. We are only looking for a number of moles. Let's see what we have been given in the question. We have been given mass, we've been given the atomic mass. In this case, we are going to use it as our molar mass. So the mass is 12, molar mass is 23. We go for our relation, n is equal to small m over capital M, and then we do our substitution, and our answer is 0.52. The next is molar volume, and it's usually for gases, and we define this as the volume occupied by 1 mole of a gas at fixed temperature and pressure. So the space that 6.022 by 10 to the power 20, that's Avogadro's number of a gas would occupy at fixed temperature and pressure. Remember, we need these parameters to be fixed. At standard conditions of temperature and pressure, 1 mole of a gas would occupy approximately 22.4 cubic decimeters, and this one, it will occupy at a temperature of 273 Kelvin and a pressure of 1 atmosphere or 100 kilopascal. So whenever we set these conditions, temperature of 273 Kelvin, pressure of 1 atmosphere, then 1 mole of every gas would occupy approximately 22.4 cubic decimeters. So here we can use a relation to find the number of moles of a gas, and that is giving us the volume of a gas per the molar volume of the gas. That is the volume it would occupy at STP. So we will have our volume per molar volume in decimeters cubed, and that's what we have there as 22.4 cubic decimeters. The next is Faraday's constant, and with the Faraday's constant, we are looking at the total charge in coulombs carried by 1 mole of a monovalent ion or electrons or protons. We know that 1 mole of every substance contains 6.022 times 10 to the power 23 particles. So if we are talking about electrons here, then electron, which is equal to 96500 coulomb and is equal to 1 Faraday. In other words, 96500 coulomb is equal to 1 Faraday, or 1 mole is equal to 1 Faraday, or Avogadro's number is equal to 1 Faraday. Quantity of charge, the column that we have mentioned there, is given as current times time. Current, capital I, and then times small t. But the unit current is measured in amperes, and then time in seconds. So we can take a problem, and the problem, so we have done all these things. Let's start with problems. The problems, it can be Faraday's constant, it can be the molar volume, it can be number of moles. So for example, in our first problem, we are looking for the mass of sodium in 53 grams of sodium carbonate. In other words, Somebody has weighed 53 grams of sodium carbonate and wants to know how much of that sodium carbonate is sodium, or what mass of that 53 grams is sodium. Okay, so with this, we need to find the number of moles, and then we'll do our mole ratio. But to find the number of moles, since it is not given here, we need to use our relation small n is equal to small m over capital M, which means we need our molar mass. So just like we have looked at, we find our molar mass here from the relative atomic masses given, and the molar mass of sodium carbonate, we now have it as 106 grams per mole. So with this, we proceed to find the number of moles of sodium carbonate, which is 0.5. Then we find our mole ratio. Now looking at the compound there, we have two atoms of sodium in the sodium carbonate. What it means is that 1 mole of sodium carbonate in the sodium carbonate, we have 2 moles there. So 1 mole of sodium carbonate gives us 2 moles of sodium atom. So if 1 is equal to 2, then 0.5 is equal to what? That is 2 times the 0.5, or 0.5 times the 2 divided by 1 of the sodium. That gives us 1 mole. So the moles of sodium is just 1. Knowing the moles of sodium, we can now use our relation for the number of moles. Then we do a change of subject to make mass stand alone, because this time round we know the number of moles of the sodium and then we know the molar mass. We are using the atomic mass as the molar mass of the sodium. So when we do such substitution, we have 23 grams of sodium as the mass in 53 grams of sodium carbonate. Another example has got to do with molar volume. We are to calculate the volume occupied by 0.25 moles of methane gas at STP. So we proceed with this. We go back for our relation. Number of moles is given as volume over molar volume. So let's see if we have been given the perimeters. We have been given the number of moles, which is 0.25. The molar volume is a constant there, which is 22.5. We do a change of subject for the volume of methane gas to stand alone. And in that case, we are going to have the number of moles multiplying the molar volume. We do our substitution and we have 5.6 cubic decimeters. So that will be the volume occupied by 0.25 moles of methane gas, given that we have standard conditions of temperature and pressure. So that is that, and we are proceeding with another problem. This time round, we are looking for time in terms of moles of electrons and current, but we will need the quantity of charge. So let's look at this one. You remember we have a relation that capital Q is given as I times T. Okay, so in order to go by that, we need to know our Q from the moles. Now we said that 1 mole of electrons would carry a charge of 96500 coulomb. So if 1 mole is equal to that, then 0.5 will carry 0.5 divided by 1 times 96500. That gives us 48250 coulomb. Knowing the quantity of charge, then we can come and use our relation Q is equal to capital I times small t. We make time the subject and then we do our substitution. That gives us 1930 seconds. So that will be the time needed to pass 0.5 moles of electrons when we are to apply a current of 25 amperes. We end the session here with questions. So please go and try these questions. And let's meet again in the next session.